Hello, it's me, Eco Chick, and I'm here at the Hayden Bridge Water Treatment Plant. And this is a super important place in our community. This is where all of our drinking water is collected from the Mackenzie River and cleaned so that it can flow through your pipes in your home to your faucet into your glass every time you turn the faucet on. So I can't wait to share this place with you and introduce you to a couple of really cool and interesting people that work here. And yeah, more in a minute.
Hi, I'm Ray Leipold, the Water Treatment Supervisor here for EWEB, which is the Eugene Water and Electric Board. And here we make sure that drinking water is safe to drink for everyone in the public. So we're taking water out of the Mackenzie River and we're bringing it into our facility and treating it, making it safe, and sending it to your taps at your house.
I'm Danielle Fisher. I'm the Laboratory Quality Assurance Senior and Laboratory Director. Here at the treatment plant, we actually do have a laboratory on site where all the water samples can come and we can do the testing and then give the results for our public water system and ensure that the water is safe.
We're here in the Headhouse Lobby of the Hayden Bridge Water Filtration Plant, where we treat our drinking water for the city of Eugene. So we're right in this building here, is the head house in the bottom floor.
How many people work to make this operation happen out here at the water filtration plant?
Right now we have about 21 people that work out here, and we work around the clock. So some people will be working in the evening and all hours of the night, and some will be here during the day. Right. But it takes people from all different backgrounds in expertise, from source protection of the river to laboratory methods to treatment process. So some of you might be wondering how we got here and why we got here at the treatment plant. And back in 1906, there was a typhoid outbreak in the city of Eugene. And typhoid and cholera were two really big issues in the early 19th century that people died from, got very sick from, and they're waterborne illnesses. And so in 1911, they created the Eugene Water Board to address these issues and treat the water so people wouldn't get sick from the water. And now that Eugene Water and Electric Board is in place, that started out as just the Eugene Water Board.
And that was because there wasn't really much electricity yet, is that right? It was like that was kind of the beginning of electrification of homes, so that was added later, is that right?
Yeah, and actually, to run the treatment plant, they put in their first electric generation system. Wow. And that's how the whole electric part of the EWEB started. EWEB was the first on the West Coast to have chlorine disinfection, which addresses the problems with typhoid and cholera, and the second in the entire nation.
Wow.
So since that has become a process used everywhere, the incidence of typhoid and cholera are almost non-existent in the United States, and it gradually went down until about the 1960s, and now we don't really see any incidents.
Wow, that's amazing. So EWEB was like an OG change maker.
Yeah.
That's so cool.
The treatment starts out at the Mackenzie River at our intake, where there are 7 pumps that can pump in over 120 million gallons in a single day. Our first treatment step is a carbon feed, which uses powder activated carbon, and we can use this for taste and odor or for hazardous algae toxins. We're at the sodium hypochlorite building. This is where we take salt and do an ion exchange and make it into chlorine bleach, and that's how you disinfect the water. So what happens is, in large tanks out back, we have salt that's submerged in water, and the part that's in water dissolves the salt, and that's called the brine. And then that brine solution is brought into these generators, which zaps it with electricity through some metal plates. And it creates an ion exchange so that it turns into chlorine from that salt brine solution. And in that exchange, there's a leftover atom, hydrogen, and that hydrogen is off-gassed into the atmosphere. And what's left is our sodium hypochlorite, or bleach. One spot that we pump it to is the beginning of the reservoir that you saw, the 15 million gallon reservoir. And that's how we kill the bugs that are in the water. So this is the one that's on.
Okay.
Those are the hydrogen bubbles
Oh, wow.
that are going up and off gassing.
I can really smell the chlorine in here, too.
Yeah.
Feels like I'm at the pool. Oh, that's so cool.
If you walk around the other side, you can see the metal plates that the brine solution goes through. See here, this is where the electricity is going through the water and brine solution. It's going down, and you can see the bubbles. It's already having a reaction,
Oh, wow.
and the hydrogen's coming out, going up, and really intense bubbles up here, right?
Wow, yeah, you can't even, I mean, it's so much that it's hard to see the movement. Wow, so this is chemistry in action.
Yeah.
Yeah.
And more chemistry for the maintenance part of this, and you can see how these get a buildup on them.
Yeah.
So operators come in here and they have to flush it with an acid solution to get that debris and corrosion off of there.
Wow. Often do you have to replace plates, or is that something that happens, or are they just continuous?
Well, they're supposed to last for 10 years. We have a spare one, so if we have any problems with them, we can replace one at a time. The chlorine bleach travels from this generator over to these 3 large tanks over here. And from those tanks, we feed with the pump and push it all the way 500 feet away to the reservoir, into that reservoir at a precise amount to kill the bacteria and bugs that are in there. Down here are the pumps that we use. So these pumps are controlled by a computer system, as everything is here, so operators can turn on, change, make adjustments to all the equipment you see here from a computer.
Do they have to do some hands-on stuff if something's going wrong, or is it all fixed through the computer system?
Well, we have operators here 24 hours a day, and there are a lot of things that are alarmed. The computer will make them aware of things that are going wrong, but then the operator will have to go and make those things right. Or sometimes it's just a matter of, we'll turn this piece of equipment off and we'll turn another one on, because we have, multiple types of equipment. One of the computers is in the building here. So this screen is for this building, and it kind of has pictures that resemble the equipment that's in here. And operators can click on these and make little changes that they need to. Chemical feed takes place in the front of the plant. This is where we can put in coagulant, and that helps the dirt bind together and fall out into the basins. So we're here in the front yard of the plant, and out here we can see our first treatment step. Down there is the carbon feed building that we looked at the map earlier. And the carbon feed building is where we add powder activated carbon, or PAC, and that's used for taste and odor that might be coming in from the river, or it can be used for hazardous algae toxins that could be coming in out of the river. And this carbon is kind of grabs on and absorbs, not absorbs, but adsorbs.
Adsorb, so what does that mean?
It's taking these taste and odor compounds, and it's collecting them in tiny little pores in the carbon.
Okay.
And then later on it's filtered out in our filters.
Okay, wow.
The two transmission mains, a 36-inch and a 42-inch, are coming up from the intake,
Okay.
where our 7 pumps are at the river, and they're pumping all that water up here, the dirty water. And right here in these vaults, these concrete vaults, is where we put in chemicals. We can put in aluminum sulfate, which coagulates and binds the dirt together. We could feed chlorine here if we wanted to, or we could do pH adjustment here as well. The valves that you see here help direct the water to different parts of the plant. So we have 3 basins, and we can direct them into all 3 of those basins, or just one, depending on what kind of maintenance work we're doing on the facility.
Okay. And how do you know what to add and when to add all that stuff?
Well, we have a whole bunch of laboratory methods that we do. We have online instruments at the river. Operators take samples and do analysis, and then we determine, what kind of chemical changes we need to do to make the whole system work.
Right. Okay. So it's all keeping it in balance. Yeah.
Here we are at the process lab for the treatment plant. Later on you'll be looking at our water quality laboratory, but this is the process laboratory that our operators use to run the plant. There's all kinds of analysis they do just for that, and our main lab does analysis for everything from the river to your tap at your house. So here, every hour, you can see these taps here. Our operators take readings of pH and chlorine to make sure that we're meeting the state regulatory guidelines for safe drinking water.
Yeah. And so that's the pH right now, 7.34,
Right.
which is really good. Yeah. Salmon would like that. What do you think, Samantha?
Once chemical addition is completed, it enters the settling basins and goes through these perforated walls where the water slows down and the particles fall out into the bottom of the basin. So here we are at the settling basins that we saw on our map. Right here is where all the first chemical addition is done, and it's all mingling together with the dirty water. And we're getting some settling coming out of here. All the big particles are falling to the bottom.
Owen, have some friends over there, I see.
Yeah, they love to hang out here.
I bet. And so what is floating in here? Is it goose poop?
No, it's not goose poop. That's kind of the stuff that's binding together.
Okay, so
know.
the chemicals are working to make it coagulate like that.
Right. There's also a cationic polymer in here, which makes really long chains of dirt and particles, and some of that stuff floats.
Okay.
And that's what this is.
Okay. Yeah, that's total science. There's always the floaters, the sinkers, and the flinkers.
The next step is the filtration process. During this process, the water goes through a sand and anthracite coal layer of media where bacteria, viruses, and protozoans are captured. So here we are at the filters. You can see the water coming in through the main gate of the filter. So in the basins, all the heavy stuff is falling out now, and the stuff that's coming into this filter is the really fine particulate. And in this filter, there's 10 inches of sand and 18 inches of anthracite coal, and that's what's going to capture all the rest of the impurities before it goes ahead and gets disinfected. So these filters run anywhere from 24 to 72 hours, and they collect all that dirt until they get clogged up. And once they get clogged up, then we have to backwash them. And essentially what that does is it sends clean water up through the filter the opposite way. All the dirt comes up out of the water, spills into the middle trough here, and it goes out to our ponds that are downhill.
Okay. And do you ever have to clean sediment out of the ponds to make room?
Yeah, we do that usually in the summertime, move it over to what's called a drying bed, and we'll dry all the water out of it. And then you'll have big equipment come in, excavators that put it in dump trucks, and we haul it over to an abandoned fish hatchery that we have across the river, and we deposit the dirt there in some old basins that are no longer being used. The next step of the process, the water drops from the filters to the clear well and goes to our large 15 million gallon reservoir. This is our rear control room. Back here, every hour, the operator's monitoring the filters and recording different things on the computer. You can see that visually they have control over the whole plant. And then this here is a representation of all the reservoirs in the distribution system. 22 reservoirs, and here at the plant we're in charge of the lower 5. We keep those full and keep the water turning over on a regular basis so that it's fresh. And then another group of people called distribution operators manage all the upper level reservoirs. In front of the reservoir, another chemical addition is done to adjust pH so that lead and copper will not leach out of pipes in your home, and to disinfect with chlorine so it will kill any bacteria, viruses, or microscopic life in the water. Here we are at a filter control center. Right in front of us is a tablet that operators use to operate filters. They can walk around the wireless, so they could go outside with them, or they could go downstairs into the gallery and work on things and still be able to operate valves. So that's part of the new technology that we see here that kind of launching us forward. with the rest of the world.
Yeah. And how long have you had those? I don't remember seeing those the last time I was here.
Yeah, we had some different ones. These are probably only about a year old.
Mobile is great because then you, wherever you are, you can look at it and it's in real time, having to make notes or something and go back old school way.
Yeah, you know, when we first computerized these, we had to have a monitor on every filter, and now we only have 2 monitors for all 14 filters.
Wow.
So we don't have to have all of that.
So super efficient. Yeah.
At the end of the process, we go to the finished water pump station, where there are another 7 pumps that will pump out water to the city of Eugene through 45 and 60-inch diameter transmission mains. So these are our 2 deep filters. They can have, instead of the 28 inches of media that we talked about earlier, this can have 65 inches of media in it, and it can basically make twice the water as one of the other filters. We're getting ready to add new media here. You can see down here these giant bags.
Oh yeah.
They weigh about 5,000 pounds.
Whew.
That's got some granular activated carbon. We'll be lifting those up with cranes and putting them into the filters. A big 15 million gallon reservoir is right in front of us here. At the beginning of that reservoir is where we adjust pH to 7.9, and we adjust the chlorine, so at the end of the reservoir it will be a 0.7 when it goes to town. We do that so that it will remain above a 0.2 at everyone's drinking water at their house. That's our goal.
Right. And you have to stretch a long ways, so it's quite a math problem, I would imagine.
Yeah, if you think about all the way out to the airport from here in Springfield, really just trying to keep pH above a certain level,
right,
so that lead doesn't leach out of pipes.
Okay.
So we're sending it out there. It's going to get higher actually the older the water gets. Just from here to I-5, you know, about 3 miles, it takes this time of year up to 12 hours for water to get from here.
Wow.
That 3 miles. So it can take a very long time. So we have to make sure the chlorine's high enough, sure the pH is low enough. You know, different things can happen to that based on the type of materials that the pipes are made out of, whether they're cast iron or plastic, or even if there's dead ends in your street. A lot of things that can change it.
So you said at this time of year it's like 12 hours to get from here over to I-5. What would the summer be like?
It depends on how much water is flowing, but probably half that. We put out about 50 million gallons a day was our peak this last summer. Right now we're putting out about 16 million gallons a day in the wintertime.
And people use more water in the summer, obviously, because they're watering outside or playing or just using more.
We're over here where our pumps are, and the 2 transmission lines are going all the way down past these homes, all the way to I-5. And the pipes themselves are so big that they hold 3 million gallons. So that's why it takes so long for the water to get there. They have to turn over all of that water that's already in the pipes. So right here, this is where the first building was. It was originally the first filter building.
Wow.
6 filters.
And that's it. And as we grow, this has to grow.
Yeah.
Yeah. Wow. Yeah, I think that's something that people don't always think about, though, is as we add more people to the planet, we have to have enough services for everyone to have a healthy living situation. And so there's more resources to consider. You've been telling us about different measurements. Are these the ones you've been talking about?
Yeah, so these are some of the different types of water we use here in the facility. So our wash water line, which washes the filters, is right up here on the top, the 24-inch pipe. And then this 12-inch blue pipe down here is the one that makes the filter sweeps and agitate the media when we do backwash.
Okay.
And the yellow pipe is what we call non-potable, so you can't drink it.
Right.
But it's used to like move chemicals around the plant and stuff like that.
Okay. So no water ever goes to waste. It
Right.
gets repurposed even if it's not potable.
Right. So every filter has all of these instruments that are talking to the computer that we looked at before. So this is telling us the cloudiness of the water, or turbidity. Yeah, we track turbidity from the upper end of the river through the plant and all the way to the tap. We take turbidity readings. These are called Headloss Transducers.
Okay.
And they tell us the pressure difference between the top of the filter and the bottom. And what that is, it tells us if it's clogged or not. So the pressure is going to go higher the more clogging that there is, and when it gets to a certain point, we backwash it. These two are our flow meters, so it tells us how much flow is going through the filter. We use a lot of flow meters around the plant because with chemistry, you have to be able to put in a certain amount of chemical based on how much flow is going through. So it's very important to know all the time what every little process step, how much flow is going through it. This is our level sensor for the filter. It tells us how high the water is in there, and that's mainly for the program that runs the backwash. It turns on things and turns off things based on how high the water level is. Part of it is it drains down the filter when we're done using it, and when it gets to a certain level, then it will, because we don't want to waste that water, we drain it all the way down to the media, and then we start the backwash. So these are all the pipes that coincide with the filter. We call this the filter gallery. These are the valves right here. They're all automated, or you can operate them by a handle as well if something breaks. So the water is coming out of the filter through these two pipes here into this main effluent pipe that goes into the clear well. And this here is called filter to waste. When we first start a filter, the water's not good enough to drink. We send it off to a tank down the hill and recycle it through the plant. And when it gets good enough to drink, then we close this valve and water goes through here and heads to the reservoir. So this is our backwash pump. This is what forces the water back up through the filters to clean them. And this can put out 10,000 gallons per minute.
That is a rush.
Yeah. So in one filter run backwash, we use about 120,000 gallons of water.
How many gallons does our city use a day, would you say?
In the winter, about 16 million gallons.
Per day?
Yeah.
Wow, 16 million per day. Huh. And what about in summer, would you say, the average? Probably varies, but...
It varies with a peak of 50, but we hang around 40 million gallons for a really long time.
When it's lower, is it more of a cleaning process because there's more sediment and stuff?
Yeah. One thing great about the McKenzie River is that most of the supply comes from spring water from the High Cascades aquifer, and that is completely off of snow and even rain. So if you've been up the McKenzie River and you see the lava beds, those are like a giant sponge, and they take in water or snow. It doesn't have to be snow. It goes down through these little pores, and then it comes out of places like Blue Pool, and that's what supplies the McKenzie River. But we're not susceptible to droughts like other people are.
Because of the aquifer.
Right.
Right. And it's a high elevation aquifer too.
The higher level of the aquifer, the more pressure it forces down
so it can force water out farther away. You see, you've got the actual aquifer way up there, but it's all these little porous rocks that prop up in places that are like around Cougar Reservoir, around Trail Bridge Reservoir.
Right. Okay.
So that happens because of how high the water is.
Right. Okay. So it's just a super shed.
Yeah.
So cool. Our planet's so cool.
We're at the emergency water treatment trailer that we have here at EWEB, and we are able to go and treat water at different places. So if not just our community, but if some other communities having trouble, we can go and help them out in a pinch. So this will treat water that's up to 10 NTU turbidity. And what we do is we have a little pump that takes the water out of the river. It goes through this system, and then it goes into a tank in the back of a dump truck. And then we can take that water to a distribution site, which is another trailer that kind of has taps for people to come and get water and take it home. And then we also have 5 well sites around the city where people can go to get water if there's an emergency like an earthquake or a wildfire or something like that, and there's no water at their home. So 5 places around the city plus mobile trailers all put together. We've got a little bit of a resiliency plan for safety. So this is my second career. I made a career change in midlife to be into water treatment, and I used to work in semiconductors making computer chips, and I wanted to get a job that was more outside, that would be meaningful, help people, and I think this is kind of what fit the bill for me. So I really liked when I was a kid playing on the river and enjoying the outdoors. So I would suggest that you try to find something that you're really passionate about or that you like, and then that's where you can go for maybe your career. Here we are at a water quality laboratory, and I'm going to pass you off to Danielle Fisher, who's the quality assurance officer, and she knows everything there is to know about the water quality lab.
This is EWEB's new water quality laboratory here at Hayden Bridge. The Hayden Bridge water treatment plant was built in 1949, complete with a water quality laboratory on site. So we've been doing on-site testing since 1949, and about a year ago, January of 2021, we moved into our new facility. So walk you through. So this first area is where the samples come in. Samples come in from the distribution system, from our watershed, or from the treatment plant, and they'll come in here and we will log them into a computer system, and that's how we track them. We give them each sample its own unique identifier, so it's a number that we add to each sample, and then that's how we track it throughout its time in the laboratory, from the time we receive it to the time that we can actually report the results. So that happens right here. We call it logging in. We log the samples in. Then we distribute them throughout the laboratory to where they're supposed to go. So if the sample is for microbiology testing, we take it to the microbiology lab. And if it's for chemistry testing, we take it to the chemistry lab. Our laboratory is split up into 2 sections. So this is our microbiology laboratory.
It kind of looks like a kitchen.
Right?
Yeah, look, complete with a stove and everything. Refrigerator.
So the refrigerator is for storing the samples.
Okay.
So for microbiology samples, they have to be stored cold. And what that does is, if there is microorganisms, bacteria specifically, in the samples, keeping them cold keeps them from replicating, changing. The main test that we do on our microbiology samples is called a coliform test. So we are testing for two big groups of bacteria. One is called total coliform, which is an environmental bacteria. It's found everywhere.
Where would that come from? Like a cause?
In water.
Mm-hmm.
So contact with soil or anything dirty, because total coliform are usually, I mean, they are everywhere on every surface.
Yeah.
That's the first main group of bacteria that we test for.
Mm-hmm.
And if the sample were to have total coliform, then that indicates that it may also have fecal coliform. Fecal coliform comes from the intestines of warm-blooded animals.
So like cows.
Cows.
And other deer,
Yes.
other grazers, and us?
Absolutely. So specifically in the fecal coliform group, we will test the sample for E. coli, which is the bacteria that we all know can make us ill. We do a test. We actually have two versions of that test. One is a 24-hour test. We take the sample, we add a reagent to it, which is a chemical food, basically, to the sample, and then we incubate the sample for 24 hours at 35 degrees Celsius. Then we'll analyze the sample after that 24-hour period. And if it is yellow, then it has total coliform in it. If it has total coliform in it, then we then analyze it to see if it also has E. coli. The other test we have is 18-hour test, which is a little faster, so about 6 hours faster getting the results. And we typically use that test for distribution projects. Say we have a main that is broken in the distribution system and we want to get it fixed, but we got to make sure that the water's clean before we hook it back up into the system. That faster test, and that just helps the work crews get the work done a little faster. Some examples of what those samples look like. So there's a couple of different ways we can look at these samples. So for instance, this is a sample that has been tested and it is still clear. So it did not turn yellow after incubating for 24 hours. So this is absent for coliform bacteria. Okay. And these samples both turned yellow, which means they both have total coliform bacteria in them. So then we look at them and say, I wonder if they have E. coli as well. So what we do is we take the sample and we put it under a UV light. Take a look. So that sample is still pretty clear. It just looks kind of yellow, right? And so this sample is fluorescing, right?
Woo.
And so what that means when it fluoresces, it means that it has E. coli in it. We treat the water here at the treatment plant and we test it before it even leaves. So we know it does not have total coliform bacteria or E. coli.
Right. Oh, science is so awesome.
It is. There's another test that we do, and I'll just kind of open up the incubator for you. It's called an HPC test. We put a special agar in those petri dishes, and it's called R2A. And so what we're testing here is HPC, which stands for heterotrophic plate count. That agar will allow heterotrophic organisms to grow. That's bacteria, molds, fungus, rusts, any type of heterotrophic bacteria, which is also a even larger group than coliform, but allow coliforms to grow and non-coliform bacteria as well. And so what that test tells us is if we have a lot of growth, then wherever that sample was taken, we know we need to go out and clean the system. A bunch of colonies of bacteria that grew on it, we'd go out and flush it. But generally, we have almost zero heterotrophic colonies, so we have extremely good quality clean water.
Yeah.
As I said earlier, if a sample comes in for a chemistry test, generally goes to the chemistry refrigerator first, then we'll distribute it in the lab for the specific testing that we're going to do. So we'll just kind of follow along. We have some different safety equipment in this lab, but this is one of the major pieces of safety equipment called a fume hood. And so I don't know if you can hear it, but this will extract any fumes. So anytime we're preparing solution with different chemicals that could be harmful, we'll do it in here.
Got it.
And it extracts all the fumes. And then we also have this piece. This is called a sash, which is where we can do work, but it puts a barrier between ourselves and the solution that we're making just to keep us safe.
Yeah.
This piece of equipment is a water bath. We use this particular water bath to do a test that's called Threshold Odor Number. We call it TON is the acronym for it. And so what it does is it allows us to test odors in water. So, you know, we all want water that tastes delicious, and so in order to ensure that it does, we'll test it for different odors. This test actually allows us to assign a number. If it doesn't have any odors, we don't detect any odors, it'll be less than 1 or 0, but if it does, it may have a number of like a 3 or a 4. If it does have an odor, we can kind of say, oh, it's kind of grassy, or it's kind of musty, or we'll be able to actually assign some adjectives to it.
Right.
So water can pick up some odors just from the watershed as it goes passing through the earth. In the fall, when there's decay of the leaves and whatnot, you can get some odors. And then there's also a thing called water age. Water sits maybe in a reservoir for a while, it might pick up some odors. So good flushing, good use of it, demand really helps with water age and eliminating odors. And in the event that we detect some of those odors, coming in from the watershed, we can treat the water with powder activated carbon. That just extracts the odor, or it even goes out to the distribution system. Some of the other testing we do on this side of the lab is a basic chemistry testing. This is a UV254 analyzer, and UV254 is a test that just gives us an idea of the carbon load. So all the organic load that might be coming into the treatment plant from the watershed. Do conductivity testing, it's just kind of a measurement of the water's ability to conduct electricity is kind of the basic idea behind that. pH testing, wherever the water lies on the pH scale, which is from 0 to 14 is the scale, and 7 is neutral, so anything between 0 and 7 could be acidic, anything 7 to 14 could be basic. In our case, we aim for about 7.9 to 8. Because on that side of the pH scale for water, that actually reduces corrosion. And the water reaches a person's tap at their house. If they were to have some, older pipes or whatever, the water is not corrosive, then there won't be any lead or copper leaching. But we try to optimize for corrosion for our customers. Some of the other testing we do here, alkalinity testing, just kind of another measurement of corrosion potential, and then chloride testing. We do some iron and manganese testing. We have a lot of iron pipes, ductile iron pipes in our distribution system, and so we will test throughout the distribution system whether or not there's iron or manganese coming from the pipes. And then we also do turbidity tests. So turbidity is really just a measurement of the clarity of the water. So the more clear your water is, the less particulate you have in it. Also, bacteria can affect the clarity of the water too, so it's a good measurement. So on this side of the lab, this is where we do solids testing. So most of the solids testing we do is specifically for our source protection program. So the group of people at EWEB that are involved in protecting our source of water, the Mackenzie River and the watershed. And so we do what's called suspended solids, total solids, dissolved solids, and settlable solids. And really all that means is that we are trying to capture the solids in different ranges of sizes. So we have 4 different tests to be able to catch them. So solids that are settlable are bigger, so they just kind of settle on their own, versus solids that are dissolved are very, very, very small, and so we have to capture them in a different way. All of that testing, and that gives our watershed people a lot of good information about what's happening in the watershed. On the other side, so this is very exciting for us. This is our Cyanotoxin Analyzer. This is a fairly new test for our laboratory. We have been doing this for a couple of years now. People may remember that the city of Salem drinking water system had an issue. I think it was 2018. There was a hazardous algal bloom that produced some cyanotoxins, and it was in their water system, and so they managed that situation. In response to that, we now have a state of Oregon regulation around cyanotoxins. And so any water system where a cyanotoxin could potentially happen, water systems that have algal blooms that could produce cyanotoxins, they have to meet that state regulation. And so we have a watershed where there can be algal blooms, And in the event that there was a cyanotoxin release, we are prepared to test for that.
So is that a newer phenomena, would you say, now that we need to have tests for it? I grew up in this area. I don't remember algal blooms being a big issue.
Right.
Like what's the deal with that?
Well, technically, the bacteria that cause the blooms are old, ancient, archaic. They've been around forever. Blue-green algae, cyanobacteria.
Yeah.
I agree with you. I don't recall hearing about algal blooms really ever when I was growing up, and I do believe that that is a product of the warming of our planet. Sunlight they get, the more nutrients they get, the
Temperature changes at different times of year.
they have opportunities to grow. Yeah, so I think that is probably why we're seeing it more. It seems to be more prevalent. Actually can test for the 3 toxins that are of interest for us and to meet our state requirements. So those are microcystin, cylindrospermopsin, and then anatoxin A. That's very exciting. And then this analyzer, this is right here. So this is a TOC analyzer, and that stands for total organic carbon. This analyzer allows us to measure the amount of organic carbon in a water sample.
Okay.
All of it, which is total, and also the dissolved component of organic carbon. Our water system has a regulation that we have to meet, a requirement that we have to meet for total organic carbon testing. We'll be doing that, and then also our source protection group likes to look at the carbon and dissolved carbon load in the watershed. And then this final machine, big, but this is actually what's called an atomic absorption spectrometer, but this is a metals analyzer, so metals and water. And so what this will allow us to do is to analyze the water samples for a series of metals. And you can see up here I've got all these different zinc, nickel, manganese, magnesium, lead, iron, copper, chromium, barium, arsenic, and aluminum. And that's just for starters. With regard to lead and copper, I'm sure we've all heard of some of the lead issues with other water systems in our country. And so there is federal regulation around lead specifically in drinking water, and that is changing and is becoming more strict.
Yeah.
And so we will be able to meet regulation. We'll be doing our own lead and copper testing. So
wonderful.
Yeah, we're very excited to be able to fire that program.
Yeah.
We definitely get our results a lot faster, as opposed to having to send it out and then wait for another laboratory to complete the results. So just to be able to respond to situations is a real benefit to our water system.
Yeah.
When I was a kid, I loved to read for fun. I would read all the time. Specifically liked reading scientific topics, volcanoes, dinosaurs, and microorganisms, and all of it. And when I got into high school, I tended to take more science classes. I took anatomy and physiology as opposed to some of the other options, and just really enjoyed science. And I just knew that when I went to college I was going to do a science track. So originally I was going to do the medical track, and I started in on that and just fell in love with the biological sciences and chemistry, and I enjoyed physics, and then some of the other classes that kind of went with that, so ecology, evolution, genetics, and decided that really biological sciences was where it was at for me. So I graduated from the U of O on my Bachelor's of Science in Biology with a minor in chemistry, and throughout my time at the university, we took a lot of laboratory courses that were required, and I just loved being in the lab. So I knew that's kind of where I wanted to start my career, was just start in a lab and see how that goes. And I started briefly for a company that manufactured paper for urinalysis testing, and I didn't love it. And so I thought, well, that's maybe not the laboratory job for me. And the next opportunity I got was here in Eugene for an environmental company that does water testing. And so I started there and just fell in love with it. It just really clicked for me. I love the chemistry, I love the science around water testing. And so I started there as a laboratory and field technician, which meant that I was testing water samples in the lab, but I was also going out and collecting those water samples.
Cool.
From different treatment facilities, from different public water systems, from different industries, bringing those samples back and testing them for a lot of the same things we just talked about. I worked there for 11 years and worked my way up to become the director of that laboratory. And when EWEB had an opening, I thought, well, I'll try it. I would love to work here at the treatment plant. It's amazing.
Yeah.
They had the equivalent position, so I applied and got it. And I've been here for 12 years. So I guess that's 23 years.
Wow.
Doing this. Yeah. So really.
So
really
you were
enjoyed
in the old lab, and this is like your favorite gift ever.
It really is. And, we say that, well, the old lab wasn't used for 70 years.
Yeah.
So that was really the goal. Like, this has to last for 70 years, which is generations of people beyond me,
Yes.
beyond
Yes.
us that will come here and work in this space.
That's
Yeah.
wonderful.
Yeah.
Oh, well, thanks for sharing that.
Absolutely.